this is what I was calling end loop. And then this is something else. So this is a branch that's branching over a statement. Here, just one instruction, but it could be more. Conditional. So what is that? It's an if statement. That's the only way you can do that. You say, well, I guess you can do it with a loop and loop one time. But that's what that is. It's an if statement. So you can write that. So now the next step is, now I know I've got these two different things, is to identify the blocks of code that are associated with the template region. So let's start with the loop. With loops, it's usually easiest to start with the exit condition, because you know right where that is. It's where it's that arrow is the end of the exit condition, and you know that it starts at the beginning of the loop. In this case, there's just one statement. Sometimes there could be more than one. So that's the exit condition. And then I could go to the ends. The step is also usually kind of easy to identify because it's going to start, it's going to end with this branch up to the beginning, to the other branch. And it's going to involve changing that. The basis of this jump will be changed by the step. So you can see it's kind of that. At least, I mean, maybe there's other things. I'm not really sure, but I know for sure that is part of the end. Because R3 you better change in here, otherwise this will be an infinite loop. So that's the step condition. Step part. What are the other blocks? What block have I left off? Initialization. Right? So I'm going to now look above the loop for providing the initial value of R3. And that's right here. Now, there's this here and there's this here that are also providing initialization. It would be okay to include them in that box maybe. But I know for sure that what I have in the box has to be part of the loop initialization because it's providing the initial value of R3 that I'm going to check as soon as I get into the loop. So the remainder inside the loop is the loop body. Then we switch over to the other template, which is the template for the if statement. I know that if statements, the initial part is a calculation of the condition on which you will branch. Right? So the condition, here's the branch, is at R5. Where is R5 calculated? Well, it's these three instructions. Those two instructions. And that is the if. And this is what? So I test this and I sometimes jump over it. What is this? Then case. Right, because I have something like this. I say, if some condition, then some statement. And it's kind of funny in a way because I'm testing a condition and then jumping over this if the condition is true. It's not the way you normally think when you read an if statement. You tend to think, well, do this if this is true. But now you see what actually has to happen. Is what you have to do is compute the opposite of this, the complement of this, and skip over that if it's false. Right? If this condition is false. This really is going to be a bunch of statements, and this statement right here executes in the then case, but not in the else case. Does that make sense? So then I'm left with a few other things. So I've got this R0. That could possibly be here. And as I said, I have these initializations here. And I have, this is actually part of the template. That was the normalization where I put the primes. So what I've done by drawing the boxes is if I just look at the boxes and not what's inside, I see the structure of a loop. So I know that's a for loop. And then when I want to know the details of each of those pieces, I look inside each box separately. So I'm never having to look at more than 5 things at once, or 4 things at once. And that's the goal. And if you're reading assembly language and you don't do this, and you're doing it wrong, what will happen is you start reading and you get lost. And you have to go back and read some other part again, and then you get lost again, and you just keep getting lost. And the reason you're lost is what I said earlier, is you can't keep enough in your head at once. So that's the purpose of structure. Now, this actually should look familiar to you. Does it look like anything you did in 110? Well, I don't know. I've been told you did something called template blending. Do you remember this? That's what this is. And so, in fact, this skill, which we're doing at the assembly language level, transfers directly into understanding big programs. So in a big program, the basic structure is explicit, if statements and loops and so on. But the coarse-grained structure, the big structure, the macro structure, that's the word I was looking for, is not explicit. That's just things what the programmer does to implement a certain algorithm or certain data structure. And so those things have templates, and you have to learn how to read code by finding that implicit structure by thinking about the template. Same thing here. So this is how assembly language is so much better than every other programming language, because even a very small piece of assembly language is completely incomprehensible. And so that was kind of a joke. It is true. And so because here even the basic structure is implicit. You have to apply that template matching and template blending, even at the level of understanding a very small program. But it's the same skill. And so, even if you hate assembly language, who hates assembly language? Who doesn't hate assembly language? It's the wrong word. It's like assembly language is horrible, and yet it exposes things that are important or something. You want to avoid it as much as possible. Go back to the slides. That's my opinion. You would never program it in assembly language if you didn't have to. That's for sure. Okay, so here's the program. And I'm going to color the things related to the loop in red and the things related to the if statement in blue. And I'm just now repeating the stuff we did. These are the different parts of the loop. Oops, and I want to stop right there. Once I have identified those parts, I can actually write the loop without the body. I know that I have some variable R3, I'm going to call it J prime. It's initialized to J, that's what I see from the first box. I know that it's decremented, that's what I see from the bottom box. And I know the exit condition is when it's 0. So I keep going until it's not 0. Keep going while it's not 0. And then I can focus, I can remove those from my field of view. I can focus on the if statement and the other thing. So here's the if statement. I have the condition, those 1, 2, 3, 4 lines are the if statement. And I can now put that inside of the loop. And I'm left with everything else, which one of them is this R0 business. And we see that R0 starts off at 0 and is incremented every step of the loop. And now it's a lot easier for me to see that because I can focus on just this stuff. I accounted for everything else. And so one way to deal with that is to add it as another variable in the loop. Right? It's initialized at the beginning and incremented, and it is used, it's the index that's used inside of the loop. So I can say, well, the loop starts with j prime at j and counts down until I get to 0. It also starts with I equal to 0 and counts up. And that's the thing I access for use to access the array. And that's just one way of doing this. It's just starting with I up to going up to j. And the reason for j prime is just so I get comparisons to 0 to the x. Okay. That step from here to here I did entirely in C. So you can figure that out without looking at the assembly language. So now I have this. And now it's easy from this to understand what this program does. What does it do?
It increases O every time a number of the array is odd.
Right. Not only does it increase, it increments. So what would be a shorter way to say that?
For every odd number.
Well, it produces a number at the end in the variable O. And that number represents what? If every element in the array is even, what is the value of O? 0. Yeah, so what it does is compute the number of elements of an array of size j that are odd. So this is the kind of thing we're going to ask you on the midterm. We give you assembly that you have to add the comments, find the structure, and then write the C code and then tell us what it does. And it will be something like this, something very simple and basic. And when you look at that, you get to see, it's very easy to see what that is because it's small and because the structure is explicit. Any questions?
On an exam, at what point is it like far enough into C? Like, if we had in like step 5 there, is that like considered a right answer, or do we need to take it all the way to the for loop?
Yeah, this is okay. So the question is, can you give crappy C? You have to give good C. And you can give crappy C so long as it's correct. Yeah. But it might be harder to explain, because we'll also ask you to explain what it does. It might be harder to do that. Right? Yeah, what's on the left is fine. Exactly. Okay, so last thing, just very briefly, we're going to talk about this. Is, the other really important kind of static control flow is a procedure call. So in Java, they're called method invocations, but in Java, they're not static. So here I have, let's say, for example, I have a procedure, foo, that calls some procedure ping, and then at the end, there's another statement. And here I have ping. And the control flow is, and then at the end it returns. The control flow is like this. You come along here in foo, you hit the procedure call, you come over here, you do all this stuff, and then you return to there, right? So this is a jump, the procedure call. It's a static jump because the compiler has generated the code for ping, so it knows where ping is. And so this step here is just simply jump ping. And then over here I have the assembly code for ping. It's, there's a label there, there's a bunch of instructions. And at the very end, I have to go back. I have to do this direction. So that's going to be another jump. And in this case, I want to jump to this address. Now the question for, like, I give you 30 seconds to talk about this, is this a static jump or not? And static jump means is there a constant here? Does the compiler know the address of the instruction that it should execute right after the procedure return? Is it static? Okay, so who says it's static? Well, if it was static, then I would have to list a number here, right? So let's consider the case of foo and also bar in the same program, both of which call ping. In the particular instance where foo calls ping, you return to the instruction X. But in the case where bar calls ping, you return to Y. And so maybe this is address 1000, and this is address 2000. What number would I put here? It's dynamic. The compiler doesn't know where to return to because there will be, if there are multiple places in the code to call ping, it needs to go to the right one. And that's a dynamic thing. So what we'll do is we're going to introduce a new kind of jump called the indirect jump, where the address you jump to is in a register. And I'll just tell you, but we'll continue this on Monday, that we'll have to compute that right here with an instruction called get PC that will take the value of the PC and put it into that register. So these two things together, and we'll come to what that means later, are a procedure called save where you are, basically, and then jump, and then the return is using that register to go back to